basically when we're looking at Thevenin's theorem and stuff, basically we're looking at this would be considered a very complex circuit, but for theory we just make it as a very as a simple circuit and stuff. But in reality, what it is it's really a very complex circuit. We're talking about the output of this. So this is called a function generator. It's for sending out AC signals and stuff like that. But we're looking at what that resistance is coming out of that output. Just like if it was on your power supply, it would be your positive and your negative leads. What is the output impedance of this device? So on a function generator, for example, it even tells you what the Thevenin's resistance is, and it says that it's a 50 ohms. Okay, so if I were to, once we go through this, and I get this all calculated out, we're going to find out that it would be approximately a 50 ohm resistor that's in series with a power supply. Since our printers aren't quite working yet, they're getting some new ones. Well, I can hand out the ones I got.
Digital isn't in charge of that, is it?
See how many we have. We'll start passing those around. Kind of share them if we need to. I'll bring it up on the screen here too. So basically, this is the schematic of this wave deck, of this function generator. And now, right now it looks very complex and stuff, but next week we're going to kind of take a little bit more closer look at it. But it's really actually broken down into several components. We have our 120 volts coming into it. It's going through a step-down transformer. It's taking the AC voltage, the step-down AC voltages, and it's bringing it down into our DC power supply. So this first block here, these first two blocks here, are just our power supply. Then we have different functions on it for setting up the different frequencies and our amplitude and stuff like that. And on our output, right on our connection where we hook it up to our circuit, this is our output. So from here to our power supply, including all the circuitry and stuff, we'd have about a 50 ohm impedance on this power supply. So on a function generator, you have about 50 ohms, and on a regular DC power supply, it's down into less than 10 ohms and stuff. So depending on what type of power supply you have, is depending on what the output impedance of that supply is. But we're going to start going over this schematic next week here, and we're going to start taking a look, because there are certain things that we can already start identifying. We have for example, in top of C7, here's the grid, C7, we have a voltage divider, and then we're using a potentiometer to vary the voltage going into that voltage divider. And so we can start identifying a lot of circuits that we're already starting to use, especially the voltage dividers. You can kind of look all over the place. Anytime you see two resistors together or more, those are all going to be our voltage dividers. And those are reference signals going into our other circuits. Then if you're in digital and stuff, if you look up in the upper right-hand corner there, you can see where it says all these U9s. This is all one chip. There's four NAND gates in this chip, but you can kind of also see, because I know Tom's been talking about the dual of the NAND gate is being shown right here with the two negated input on the OR gate. And so that's the dual of that NAND gate. So depending on what they're doing for their circuit, they might draw it up as the dual, or they might draw it up as the actual NAND gate there. So we can start identifying a lot of the components that we're seeing on here. And by the time we get to solid state and op amps, we'll pretty much cover every component that's on here. anywhere from switches to op amps, comparators, oscillators. And so we're going to be looking at all those components. Bridge rectifiers, a lot of those components. So when we're looking at these, the Thevenin's resistance, and we're kind of looking at what it would be for this whole complete circuit. Okay. Now, when we really did Thevenin's theorem on this circuit, it would take us probably take you a year or so. So I'm going to show you a shortcut of how to figure out what your Thevenin's resistance is on this circuit here. And there'll be a couple labs on it too. All right, so let's go back to the circuit here, and we'll kind of hang on to those schematics, and we're going to start using those as references and start showing you how to look at schematics, how to troubleshoot schematics. And if we break it down into individual modules, you'll find out that it isn't really all that difficult to troubleshoot, as long as we have enough information. If we know what the test point voltages should be and stuff like that. All right. So here's our, so we're going to do our first Thevenin circuit here. And even without even knowing what the heck you're doing, again, just like our labs, if you just follow the procedures, you can come up with an answer. The real important thing is to kind of understand, why is it that we want to know that, and what's the purpose of it. All right. So when we're analyzing a circuit, we know that it's always good just to kind of understand what's going on with the circuit to begin with. We know that all my current is going to be coming out of the power supply, and then all these grounds can be all tied together. This is all one. Those are all one point. Okay, so I got all my current coming out of my power supply. It's going to come into the first current node. I got some current going in through R2. Got the remainder of my current going up into my load. And then that's going to come in through R3, and that's going to combine with R2. And then my total current then is going to be going through R1. And then back into my source. Okay? So I always recommend definitely start, making sure that you draw your current paths and polarities and, find out what's going on with your circuit. All right, so then to come up with a equivalent circuit for this circuit, we can take this circuit, whether if it's as complex as the WaveTech or as simple as this circuit, we can reduce it all down to one voltage and one resistor, and no matter what I do to the load, it'll act the same way as if I were to put it into this circuit. And so I can reduce it down to just to one voltage source and one resistor, and have it react the same way. So let's follow the steps here. So all we're going to do is just follow right down the steps. So it says the first step is just says remove the load. So we're going to just go ahead and we're going to remove the load right here, and then it says determine the voltage seen by the load. Okay. So we'll just put in our voltmeter here. And we're going to measure and find out what is the voltage across that. Now remember, when we measure across an open, what are we actually measuring?
Source voltage.
Our source voltage, okay? Now remember, our source voltage is if we have a series parallel circuit, it's the voltage that's going in after the series circuit. So again, so it's still kind of complex to really kind of find out what we really actually have going on. So sometimes it's just easier to go ahead and straight line your circuit so we can see what's going on. So I'm going to put my power supply on the left-hand side. Come down, I'm going to force myself to go up. So my current came out of my power supply, came into my first current node, and it split two different ways, went to two different branches. Some of my current went through R2, and some of it went across my load. Now when we're talking about the load, that's going to be our load, that's going to be our external device that's outside the power supply. You know, my load would be whatever being hooked up to this connector here. Everything else like R2, R1, and R3, that's all part of the internal makeup of the circuit itself. So then went up through RL, through our load, and then RL went into R3. And then those two currents then combined together at R3 and R2 there. So then we're just going to join those back together. And then it's going to go up. Then all the current is going to go back and it's going to go through R1. And then back down into my source here. Okay, so that's what our equivalent circuit looks like for that circuit. So then we know that, again, all my current is going to come down, it's going to go through, it's going to come up, it's going to split, just like we said there. Some of my current is going to go through R2. Some of my current is going to go through my load and through R3. And then those two currents are going to split. And then they're going to go up, go through, back into my source. All right, so right now you can see that we have what type of circuit do we have? A series parallel circuit. Okay, so then we went ahead and we followed the first step. It said remove the load. So we're going to just go ahead and we're going to remove the load here. What do I have? 20 volts. So we're just going to go ahead and remove that load right out of there. And then we're just going to replace that load and we're just going to put in our voltmeter across there. Okay. So now with our L out of my circuit, would I have any current going through this branch? No. I have it open, so there's no current path other than when I hooked up my voltmeter. Now I have a little bit of current going through there, but that's measurable. We don't have to worry about that. We can just consider that as an open. So realistically, this circuit here isn't even there because we have an open. R3 is not even part of the circuit. There's no current going through there. So the only current I have going through now is coming out of my power supply. It's coming through. No current can go this way. So that means all my current must go through R2. Then it's going to come into here. There was no current here, so it didn't combine with anything, and then it went through R1. So now what type of circuit do we have? A series circuit. What's another name for a series circuit? Voltage divider. So R1 was okay. So now basically, did everyone get your little YouTube thing here? I'm going to erase little Mindy's notes here.
What was it again?
So what we're going to do now is we can just go ahead and draw up. If we can't see it this way, we know that we have no current going through this circuit. So basically our new circuit looks like this now. Still have our source. So that's what our new circuit looks like. So we have all my current going through, all my current's going to go through R2, it's going to go up, it's going to go through R1, and then back into my source. Alright, so now what our next step is now we need to figure out, so the question is what's that voltage that's being measured across the load with it being removed? So the first step we want to do is that we want to figure out what our voltage drops across R1 and R2 are. Now we're going to do it without using currents, like I said, when we were doing our troubleshooting and stuff like that. typically we're never going to be looking at our currents and stuff. We're just going to be using our voltage divider formula. So take your voltage divider formula and divide up the voltage amongst the two resistors. Which one's going to drop the most amount of voltage?
R2.
R2. Okay? So figure out what your voltages are across R1 and R2 are.
R1 is 8 volts, R2 is 12 volts.
So we have 8 volts going across R1, and then 12 volts across R2. And if we add up the two voltages, sums of both of our voltage drops does equal our source voltage, so we have a pretty good indication that's correct. Also, we know that the 1.5 kilo ohm dropped more than the 1 kilo ohm, so we probably did everything okay. All right, so now we have our voltage drops. So if I were to take my voltmeter and go from this point to this point, what would I measure for voltage?
12 volts.
12 volts. If I go over to here, how much voltage would I measure? 12 volts. So that's my source voltage going into that parallel circuit. Even though I have it open, it's still part of our circuit. It is a part of our circuit. There's just no current flowing through it. So my source voltage going into this parallel circuit is going to be my 12 volts. So what would I measure across my load then for my across RL? What would be my voltage across here?
12 volts.
12 volts. Because what do I measure across an open? My source voltage. My source voltage going into that parallel circuit is 12 volts. So I'm going to have 12 volts. Not my 20 volts. My 20 volts is my source for my complete circuit, but not my parallel circuit. So I'm going to end up measuring my 12 volts. And so then it says determine the voltage seen by the load. So then we know that we're going to have 12 volts. Okay, so that's our first step. Now it's going to say, now what it's going to do is we're going to replace the voltage source with a short and then determine the resistance seen by the load. So that means that what it wants us to do is that we're going to put it and short that right across. Now when you're doing it in the lab, make sure you don't short out your power supply. Remove it first and just replace it with a short. Don't put a jumper across your power supply, otherwise you're going to short out your power supply. Now what it wants us to do is find out what the resistance seen by the circuit. Well, now the circuit's kind of changed a little bit. Okay, did everyone get this all down? This is going to go away here. All right, so we're going to do it all over again. So then what I'm going to do is I'm going to replace my voltmeter with an ohm meter. Now remember, these ohm meters have their own internal power supplies, and they're going to be setting a current going through here. So for example, we can put our positive and negative of our ohm meter. It really doesn't matter when we're measuring resistance since there's no polarity, but to give ourselves some kind of direction to find out how to reconfigure the circuit. So our ohm meter now becomes actually our voltage source for this particular circuit. So I'm going to draw in our ohm meter here. That's going to be our voltage source. So when I'm looking at this, I'm trying to figure out what type of configuration do I have now with my power supply being shorted. So now my current is going to come down out of my ohm meter, come through my grounds, and it's going to still split up. Some of it's going to go through R2, some of it's going to go through the power supply that's being shorted out, through R1. Those two currents are going to combine, and then all the current is going to go through R3. So I'm just going to re-sketch that out. So I got The negative side of my ohm meter is coming down, going through the ground, it's coming up. It's going to split. Some of it's going to go through R2. And the remainder is going to go through the shorted out power supply. We'll just draw that in there so we know where that's at. And then it's going to go through R1. Then those two currents then are going to combine back together. And then all my current then is going to go back through R3 and back into my ohm meter. So then I'm going up to R3, back down. Now I have my R3. And it's R1. All right, so now what type of circuit do we have? Series. We've got one series and one parallel. Anyone want to combine the two? Oh, series parallel, did you say? Okay, yeah, series parallel. So what we want to do then is we want to get it down to our equivalent, so if I put my ohm meter across this, what would I measure for resistance? So we want to make up our equivalent circuit. So what resistors can I combine to begin with?
R1.
Yeah, so we can combine R1 and R2 and make that into one resistor. So once I combine R1 and R2, I'm going to combine those by being in parallel. R3 is so what do I get for, what do I know too on this parallel circuit? What do I know that my resistance is going to be? Less than 1 kilo ohm. Okay? So we want to combine R1 and R2 using the parallel formula. What do we end up getting for resistance for R1 and R2?
600 ohms.
600 ohms. Okay? So now I have what type of circuit?
Series.
Series. And I want to get it down to one resistor, so if on a series circuit, what do I need to do to my resistance?
Add them together.
Just add them together, and I can come down to one single component. And that value then is, after I add them together, is going to equal what?
Total resistance.
Yep, the total resistance, and that's going to equal what?
1.8K.
1.8K. Kilo. So there's my Thevenin's voltage. There's my Thevenin's resistance for this circuit. So that's all the farther we have to go with that. We've got all the information we need. We'll go ahead and wipe off this here. So what my equivalent circuit looks like now, if I took this same circuit and I had a 12 volt power supply, 12 volt source, and I put a 1.8 kilo ohm in there, this circuit would react the same way as this circuit would. So for example here, so we'll put our load back in there, and our load was at 1.8 kilo ohms. Not to be confused with this one, I'm looking at the load itself right here, RL. Then what's going to be my current going through my load?
$503.3 microamps.
Say that one more time, Bob.
503.3 microamps.
503.3 microamps. So you get 503.3 microamps going through my load. So whether if I put it into this circuit, if I were to turn it in the same circuit as this one up here, I would still end up with 503.3 microamps going through that load also. So what is my voltage going across my load? So what type of circuit do I have here? Series. What's another name for a series circuit? Voltage divider. If they're both equal to 1.8 kiloohms, 6 volts.
Where did you get the current? How did they come?
Sorry, I made a mistake on the current.
That's what.
Oh, you know, I kind of jumped ahead here.
You can't do this.
Yeah, my fault. Okay, ignore the current here for now. Again, I do shortcuts that forget to. Yeah, so first of all, we should find the voltage going across our load. I should put a line in there because I've done that before. So first of all, find the voltage across your two resistors, so we know that my voltage across my load is going to be my 6 volts. The voltage across my Thevenin's resistance is going to be 6 volts, since they're both equal. Now we have enough information to find my current. And so now we just take our 6 volts divided by our 1.8 kiloohms, and what do we end up getting?
3.3 milliamps.
3.33 milliamps.
3.3 or 3.33?
3.3.
Oh, I see, yeah.
Okay, yep, so it's just our 6 volts divided by our 1.8 kiloohms, and then we're going to get 3.33 milliamps. So that would be the same thing if I hooked it up to this circuit. I would get a voltage drop across my load that would be equal to 6 volts, and I would get a current of 3.33 milliamps. It wouldn't matter which circuit I hooked it up to, I would get the same thing. So I can reduce this whole complete circuit down to one power supply and one resistance. That resistance, this resistance is my output impedance of this circuit. Okay? So how much current do I have going through my Thevenin's resistance?
3.333 milliamps.
Yep, 3.33 milliamps, because what remains constant in series circuit? Current. Okay? So you can see that, that's my voltage is dropping across each one of them. My current is the same. So at that point, this is where we're calling it. This is what we call our maximum power transfer. This is where we're getting the maximum amount of power that RL will ever see. I always get my maximum power transfer the minute that RL equals my impedance of my device, whether it's this circuit or whatever, or if I'm doing Thevenin's equivalent. The minute that my RL matches my Thevenin's resistance, I'm going to get my maximum amount of power. So let's take a look at a little bit about that, because that's kind of an important thing. And that's kind of the whole idea of Thevenin's resistance, is to find out what our maximum power is, especially if we're into broadcasting wirelessly or whatever we're doing. We want to make sure we get the most amount of power coming out of our antenna, because this RL could represent an antenna, which is an electromagnetic energy. Okay, doesn't necessarily have to be a resistor. It could be an antenna, which is electromagnetic energy that's being put across our output of our thing. So, this would be kind of our, we could say that's our VL. This is our output terminal of our device.
We wouldn't.
So let's take a look at that circuit a little bit deeper. So if we want to verify that my Thevenin's resistance is actually 1.8 kilo ohms, if we wanted to do it in the lab and verify that it actually is 1.8 kilo ohms, what we can do is we can configure ourselves a potentiometer as a rheostat. So when we, and you're going to do the, if there's somewhere in the lab and it's asking for a certain value of a resistor and you don't have one, we can always configure our potentiometer as a rheostat. Okay, so if I put my ohm meter across here, okay, if I put an ohm meter across here, and let's just say this is a 1 k ohm potentiometer, with my wiper all the way to the left, how much resistance would I measure?
1 kilo ohm.
1 kilo ohm. Okay, I'm going to have to go through all of my resistance to get to the other side of the ohm meter. So I measure 1 kilo ohm with my wiper all the way to the left. If I take my wiper and I move it all the way to the right, now what am I going to measure for resistance?
0 ohm.
0 ohms. Yep. So now I got a range from anywhere from 0 ohms to 1 kilo ohm. And if I put it halfway in between, what would I end up measuring? Yeah, 500 ohms. Okay, I'd measure half the resistance. Okay, so I got a range. I can go ahead and I can just kind of set my range on it from 0 to 1 kilo ohm. So if I need something, so for example, if we wanted to verify that what's going on with the circuit, I need to make sure that I have something, a resistor that's larger than my 1.8 kilo ohm. So our next available one that's probably in our parts kit is probably going to be our 5 kilo ohm. Okay, so we can just take our 5 kilo ohm potentiometer, wired it up as a rheostat, and now we have an adjustable resistor. We can go ahead and verify that. We can tune in that resistor to be exactly the resistance that we want. All right, so if we want to verify that this is actually going to be our 1.8 kilo ohms, and our Thevenin's voltage was 12 volts. What we want to do is our first step that we want to do is, we're assuming that we don't know anything about this power supply. So our first step that we want to do is we want to go ahead and remove our load from there. And then I'm going to remove my load from my actual circuit, put in my voltmeter, and I'm going to measure my voltage across the open. And what would I measure for voltage?
12 volts.
12 volts. On step 1. Okay? So then what I'm going to do is I'm going to put in a variable potentiometer. And I'm just going to set it down to five kilo ohms. Okay, I'm going to give it the maximum amount of resistance to begin with. So I'm going to start out with 5 kilo ohms. So between my rheostat and my Thevenin's resistance, which one's going to take the most amount of voltage?
5K.
5K. This thing's going to almost take twice as much than what this one is. Okay, so we know that this one's going to be approximately. We're going to do some approximations because that number is not important for us. But we know this one's going to probably drop somewhere close to probably about 9, maybe about 9 volts, or somewhere between 8 and 9 volts. And this is going to drop anywhere from 4 to 3 volts. Okay. So if we're just looking at our graph, here's my X. This is going to be my voltage. So from 0 to our maximum voltage that we can never get, 12 volts. This is going to be, let me change that around. This one's going to be my voltage from 0 to 12 volts. And this will be my resistance of, we'll call this one our RL. So that'll be my resistance of RL. That's going to go from 0 ohms up to 5 ohms. And we're going to kind of work our way backwards, because typically when we're working on circuits, we normally like to have the most amount of resistance and then start decreasing it. So we're going to kind of work our way backwards. We never really want to put a short into something unless we really know what's going on with the circuit. So we always want to try making sure that when we're analyzing a circuit and we're using it with a potentiometer, that we always have it so that it's at the maximum resistance. But then sometimes that means that we have to graph our stuff kind of in reverse order. So we're going to graph out the function of RL here, which is in our resistance. We know that we're at 5 kilo ohms, and we said that we were going to, we'll just throw a number in there. We'll just say that was turned out to be about 9 volts, because we knew that it was going to be at least well, it's about more than twice that. So yeah, let's say about 8 volts, just for approximations. So when my load was set at 5 kilo ohms, so here's my 5 kilo ohms, here's my 8 volts, here's where my voltage was. Voltage of RL. Okay? It was, so now with my having my maximum amount of resistance in this circuit also, what happened to my current? Is it increased or decreased? Before it was 1.8 kilo ohms, now it's at 5 kilo ohms. So what happened to my current?
Stayed the same. Decreased.
It decreased. Yeah, because my total resistance of the circuit is now what? 6.8 kilo ohms. Okay, so my current is at its minimum that we can for the 5 kilo ohms. And we'll just say, we're just kind of doing some rough. We're just going to say that my current is low. So my voltage is high, but my current is low. As I start increasing my potentiometer and I start decreasing my resistance, going from 5 kilo ohms to 0 ohms, what's going to happen to my voltage across my load?
It's going to drop.
It's going to drop. So my voltage is going to start to drop. And again, we're just kind of doing some rough numbers here. We're not going to recalculate everything out. We've got a lab for you to do that. So that's going to start to drop. As I start decreasing this resistance here, what's going to happen to my current? That's going to go up. So then my current is going to start to go up. So that's what my curves are going to look like. Here's my voltage. It's going to start out very high and then it's going to go low. My current is going to start out very low and then it's going to start going up. Right at this spot, right when I get to this spot, right where those two intersect, that's where my voltage and my current are both at their maximum for when they cross. That's where I'm going to get my maximum amount of power. I'm going to get my maximum amount of power right at that point. Anything above and below that, my power is going to decrease. At this point here, if I go from my 0 ohms to a particular number, I'm not going to have as much voltage, so remember that my power is equal to IE. So my voltage has dropped. Even though my current went up, my voltage dropped more than what my current increased. So my power is going to be kind of low on that point. As I hit that peak power, then my voltage goes up, but then I lose my current. And so then I'm going to start losing my power again. So now you should recognize that graph from your, I think it was lab 6. That's your power curve. Okay? This is what they're trying to get you to go on into. How do we graph this out so that we can understand when we're working with stuff like this? We've already done it. Now we don't have to go over the graphing of it. We might not understand what the graph is representing, but we know how that graph is. Now it makes a little bit more sense what that graph is representing. So we end up getting this power curve. Okay? So my maximum amount of power then happens when my voltage and my current are at their peak. And that's where that's where I call it as being my maximum power transfer. That's when this RL is getting the most amount of power. And then what is this voltage at this point right here? 6 volts. What's my resistance of RL at this point? 1.8 kilo ohms. So I'm going to get my maximum amount of power when my load matches the internal resistance of my device. And that's our maximum power transfer. And so another name that we call this is half power, because half my power is being dropped across this, half my power is being dropped across this, and the sum of those two powers equals my total power. And that's another name that we call for half power, and we're working with that in AC a lot. And so these are our power curves. Power isn't linear as my current and my voltage increase. So again, sometimes we have to work our way backwards. A lot of times we do it this way when we're working with our circuit, when we're working with our labs and stuff like that. But out in the field, though, we always like to start out so that we have the minimum amount of current. That way, as we start decreasing our resistance, if all of a sudden our current starts to go high and we don't want to do any damage to our source, all of a sudden we can kind of go ahead and stop the experiment and just say, oh, something's not quite right here. But I would go ahead and I would just start tweaking this up. So what I would do if I wanted to find out what my Thevenin's resistance of that is, a quick way of doing it is I'm going to put my voltage source right across here. And if I want to find out what my maximum amount of power transfer is to the circuit, I'm going to be watching for my voltmeter to get to 6 volts. Because I knew in our first step there, we said that when I measured across and open, I said I got one for measuring across the open of RL. How many volts was that when I said I measured across the open?
12 volts.
12 volts, right? Okay, so unloaded it was 12 volts. So I know that that's what my source is, my internal source of my devices is at 12 volts. I know that that's my internal source. So what I want to do is I want to start increasing my wiper here until I get half the voltage of whatever my source was when it was open. So I'm going to just start tweaking out my 5K. I'm going to keep on tweaking it, and it's going to go from, it's going to go 11, 10, 9, 8, 7, and all of a sudden I hit 6. I know at that point I'm half my voltage of my source. At that point I know that I'm at my half power point. I know that I'm at my maximum power transfer. So I watch my voltmeter and I see that it says 6 volts. Then what I can do is I can go ahead and I can remove my potentiometer from my circuit. Remember, for measuring resistance, you have to remove that component out of that circuit. You don't want to move the wipe or anything, but now I'm going to go ahead and I'm going to put my ohm meter in there. And I'm going to measure that resistance. And when I measure that resistance, it's probably going to equal what?
1.8K.
1.8 kilo ohms. I know that it's going to match the internal resistance of my device. And at that point, I know that my impedance is matched to the impedance of my thing. I know that at that point, then anything at 1.8 kilo ohms is going to have my maximum amount of power. That's when I'm going to be able to emit the most amount of power coming across my load. How was that? Does that all make kind of sense? Really? Well, like guys, you have to explain it to me. Yeah, so remember that these circuits are very simple when we're looking at them, just so that we can follow the procedures. Like I said, anyone can follow the procedures and come up with these numbers. But what's the purpose of the whole lab? This is the purpose of that. And you can see that if we were to do something, a full-size thing, how complex it could be. So what I could do then, okay, anyone have any questions on this before I erase it? Okay? So I'm going to erase all this. I'm just going to bring up the schematic here. So here's my output of my function generator. This is the output of my function generator right here. This is going to be hooking up into this BNC connector. And the first step I want to do is, so if I don't know, or if I want to verify that this is 50 ohms out, the first step I want to do then is I'm going to go ahead, and this outer ring is going to be my ground, and then the center one is my source. So what I'm going to do is I'm going to hook up my voltmeter and hook it up from that center pin up to the outer ring of that connector. And I'm going to measure the voltage. And that voltage is going to give me some number. So we'll just say depending on what the amplitude is set at, I don't know, we'll just say that it's
10 volts peak to peak.
all right, 10 volts. Sounds like simple numbers. I was going to go with 13.56, but but if you want to keep it simple, that's fine with me. I don't care. So let's just say 10 volts. So then what my next step then is, so now there's my voltage of it being unloaded. Then I'm going to just go ahead and I'm going to remove this, and then I'm going to put in a rheostat across my output. I'm going to drop that